together. Next slide, please. So when you're considering a ligand or a synthetic organic molecule for use, what are you looking at? You're looking at one, strength. How strong or how robust is it? Then the next one is selectivity. Selectivity is a very important component because it gives you an indication of what do you want it to react with. So that's a very important component. Then the next one is speed. Are the kinetics of its reaction appropriate? Are they well or are they good enough? Or phase. So therefore you have a compromise system. Specific formulation reaction, whereby you just have your starting phenol. It can be any, so long as it is para coordinated. So when you have that phenol, you can actually react it using a Grignard reagent. I think this is basic chemistry that you run in your high school. Anybody in Alishika chemistry, you are able to know that there's a Grignard reagent, so you can actually make it. That is methyl magnesium together with methanol, and then therefore you have a Grignard reagent, and therefore you are able to form that catalyst. Then that catalyst reacts to form an intermediate. Can I get next? Next? Yes. So that catalyst now is able to react in between the two phenolic groups, combining on the phenol group, and therefore then adding on to the formaldehyde. Once it's added to the formaldehyde, and it is very specific, it goes to the ortho position of that phenol group. So therefore, next. Yes, therefore you get your product. So this is basically your salicyl aldehyde, which is basically this particular molecule here, this one here. So that is the first step. Then the next step is that once you've made that, you are able to now use your normal condensation reaction. The guys who are doing chemistry, I think they'll be able to pick on that very easily. Condensation reaction is very simple. You take an amine, you react with an aldehyde, it releases water, you end up getting a very good, nice looking molecule. Next slide. So you are able to get these nice looking molecules. You see that? There are so many of them that you can play around with them. You can play around with them as much as you want. You can have one that is not substituted. That is the group here. It's not substituted. You can have which is with an electron withdrawing group. That's a methoxy group. You can have one with a tert-butyl group. You can have one with a long chain nonyl group. You can have a phenyl naphthyl group. So all those things you can play around with it. Next slide. You can now again play around with them by adding different amine groups. So those are precursors that we normally use. So you can play around with those ones, and therefore you get different permutations of molecules that you have. So you can actually have a whole range of molecules that you can use, and I'll explain how they're being used or what we mean by industrial application. So these are the different aldehydes, and then you have different imines that can be used. You can see that this is a triimine that you can actually also be able to use, as opposed to the primary and secondary imines. You actually use amine, use tertiary amine. The next, so this one here is just a basic FTIR. So once you've made it, you do your normal characterizations. That's the FTIR. You can see the imine groups. Next, you can see the imine. You can see some of them are blue shifting, some of them are red shifting, and that is just normal in terms of chemical synthesis and or characterization. The next one, those are the aromatic aldehydes, aromatic protons. You can see them, how they're moving. That one indicates that you've actually made the product. Once you start seeing the imine, because you remember you have an amine. So when you start seeing the imine, you know that, you know what, I'm good. So I've started making the right product. The next one, you have your NMR. Next, you can identify your imine, the imine proton. Next one, you have your aliphatic protons there. You can analyze them on NMR. Next, okay, so again, the aliphatic aldehyde, that's the one next to the oxygen. You can actually be able to see which one is where it is. Next, this is the carbon NMR. So carbon NMR, you can be able to pinpoint where the imine hydrogen is next. Those are the imine proton. When I talk about imine proton, just next. The imine proton is basically the one that is next to where there's double bonded nitrogen, and then there's a proton on top of it. That's a very important one because it's very, very weakly. It's one of the most active one there. So you'll see why and how, because it's a conjugate system. Conjugate systems means that there's a delocalized system in the whole of that molecule. So therefore, those ones become very important. So you can actually see the next one. You can use the mass spec and be able to analyze mass specs. That is basically to give you an indication of how the molecule fragments. And you can see that the molecules have got different fragmentation patterns. Next. Then finally, you get the crystal structure, which now tells you what you've actually made. So those are just basic analytical techniques that we normally use for organic synthesis, in a sense. So next. That is the internal arrangement of crystals inside the lattice of the molecule. So when you have a crystal structure like this one here, they have special arrangements inside the lattice. You know, like if you get a sugar molecule, right? What you don't know is that you can actually use a chemical technique which is called single crystal X-ray diffraction, and you're able to pinpoint where each carbon atom is, where each oxygen atom is, and how they are linked all together. So that if that crystal is not perfect, you are able to even tell that, you know what, this crystal is actually not good. We use that a lot for identifying of specific compounds. So you are able to know, okay, you know what, this is the right material. So those molecules are arranged in a special arrangement in the lattice of a crystal. That is under structural chemistry. So you actually are able to do that. It's what they use to do morphs and all of you, so that the spacing around them, I'll show you how. Analysis basically in terms of analytical techniques. Next. So this imine-based ligands, I'm only working on one. I'm not. Application is in hydrometallurgy. Now, we all know mining, right? And whenever you think of mining, you think about those big machineries. You know, everything is hot and what have you. But there is a different kind of mining. The first one is, of course, pyrometallurgy. That's why you see the big machine. The next one is hydrometallurgy, meaning water, and use just water alone. So the system is much compressed. It is not as hot as the other ones, okay? Then you also have another, I think there's a question on that, which is called phytometallurgy, whereby you use plant to abstract metals, mining metals, plants. So the metals just comes out of the plant and it's picked from the leaves. That's a unique technique, and I think there's some people that are working on those ones. So here, in terms of imine solvent extraction, you use a very, very basic technique. If you remember in your high school, you would take two immiscible solvents, right, in a separating funnel, right, and you say that this one is water, this one is what? This is any organic liquid like kerosene, right? That is the very basic technique we are using. So what happens is what? Is that you take it and then you put this ligand specifically in the organic phase. But what happens is that now on the water phase, where the molecules, on the water phase, you take your specific metal, you dissolve it, in a sense, okay? Once you've dissolved it, the metals are going to be all dissolved with all the waste inside there. But these molecules are so specific that they only react to only one metal. Meaning that if it is gold, it's going to react with gold. So it takes that gold from that organic phase, aqueous phase, and takes it down into the organic phase. That is if you're using a solvent that is much denser than water, that is like DCM. Or if you're using kerosene, you can use kerosene also. Kerosene is going to move into the upper organic phase. So therefore, you are able to take that molecule, and it's only that one metal. So therefore, the other waste is just discarded. Then this particular metal that you have abstracted into the organic phase, you take it into another phase again, and then it's abstracted again into the liquid phase, and then you just remove the water, and you have pure. Now, this technique, while you look at it, it looks very basic, but you see that the first large-scale application of excess was for the Manhattan Project. The guys who understand politics knows what Manhattan Project is. Manhattan Project was the one where the Americans designed the first nuclear bomb, atomic bomb in a sense, okay? So when they wanted to separate those very radioactive materials, they could not use heat. So what did they use? They came back to this principal technique. And therefore, from there onwards, now it became up and picked up very fast. So now it's actually one of the most used techniques, particularly for mining of copper, nickel, and such kind of things. So you basically use that technique a lot. But in the nuclear world, it is the principal technique. You're not going to use heat kuchemsha something that is radioactive. Okay? So it's the principal technique for that kind of things. Let's move next. Next. Yeah, and you can see that this is basically the engineering setup in which that they use it, where you have your metal leaching in an acid, then it moves into the metal extraction, and then you have the metal stripping, and then you have the pure metals produced, which is the way mining works, basically. And so where our focus is in that box, basically. That's where our molecule plays the biggest role. So one, the molecule that you're making has to be able to what? Do the extraction. Two, it has to be able to do what? It has to be able to be stripped of that metal. And therefore, the molecule is just circulated in the system continuously. So you have very, very unique system whereby it's very cheap now. You don't need to use all those expensive, it's greener, and you have all those technology which is much better. So we move forward. Next. Yeah, this is one of the known extractants that is actually commercially sold. This is called an oxime ligand. And if you look at it, it looks very much like one of ours. But if you look at ours here, this one of ours is much more, is much better one because of the chelate effect. People know chelating, right? Chelating effect is whereby if you have the different donor groups, what happened? It binds much stronger than one which is, because if you look at this one here, this is just two donor group. You see this is oxygen and nitrogen. Then you have different functionality. That is the one that we have. Go back, please. That's the one that is here. This is actually sold by BASF. It's one of the world's largest mining producers of this compound. So where the lab where I was, we were actually getting any new material, any new ion exchange that is produced, they would send it to us to test its parameters. So knowing that, we came up with these molecules here, which are much better, okay? So then let's move forward. Yeah, so this is like an example of the extraction that we get. This one, there's a reason as to why this is very low like that. This is about 16%, this is 14%. The donor groups, they play a critical role. One of them is that once the donor groups are very, like the nitrogen, they tend to get very, very soluble in the aqueous phase. The compound that it forms leaches back into the aqueous phase. But that is not a problem to us because we actually have techniques to removing it from that aqueous phase onto the organic phase because we want it in the organic phase. So you can actually see that one of them is getting about 80% of copper and then 66% of lead. You see that? So they are very, very selective. And you know, this is in a mixed metal composite. You'll have all the metals, like all of them, it just picks those two. Okay? So you can have different one and then you just test them. Next. One of the things that has been talked about here is the effect of pH. What role does the pH play? pH is very important because look at that. This is this molecule here. If you look at between 2 to 3, you are able to remove all, like if I have copper and how do I separate the copper and the lead? I'll use between pH 2 to 3, look at how much I'm getting out. I'm getting out 80% of the copper. So I don't need to move much further, but if I continue, go back. If I continue moving the pH longer, then I can actually get now what? Because if 80% of the copper is out, how much do you think is remaining? Very little, right? So therefore, when I move pH from pH 3 all the way to about 5, I'm now able to remove the lead. So by playing around with the pH, you are able now to remove those things sequentially. Like I'll do the copper first, remove it, then do pH what? 3 to 5, then be able to remove it. Like that. Next. So this is transport study. This is a setup whereby you can actually do both of them at the same time. Next. So this is the setup. Here you're using now a triphasic system. 3 phases. 3 phases in the sense that you have an almost like a centrally located container, right? That container, in the middle of it, it is connected onto an organic layer. So the water is just in the center, in the center there, with your whatever analytes that you want to remove. That means that it has got the metal mix, right? Then, on the base of it is the organic phase. On the other end of it is now your stripping solution, which is just a water at a lower pH, pH1, pH2, okay? So what happens is that this system here, when you start it, the metals are going to leave this upper here, come into this organic layer, right, in one phase. Then they're immediately taken out because they're going to be, you see this one here, there's a membrane here. So it's called bulk liquid transport that you can actually use to mine your metal. So it's a one system flow so that you can actually just have it running continuously and you're able to get very good results. Let's move to the next, I'll show you the results. Look at that. 23% of the copper were taken into the membrane phase. But out of 23%, the ones that came out onto the stripping phase in that triphasic system is 22 ppm. Meaning that it is almost 100%. Move next. You can see that is almost 100% stripping. The ones that are getting in, they are immediately taken onto that, and you have a complete system that you just keep on adding the metals, and then the other side you keep on doing what? Taking out fresh solution. And so you have that kind of setup that is continuous. Let's move next. So this is in terms of structural chemistry that I was talking about, coordination chemistry. Let's move on. So when these things react, they react in specific ways, and there's a reason as to why they do that. It's one, because of the donor group. Two, it's because of the unique nature of those ligands. It's called a bite angle that they have. Bite angle tends to be, when a bite angle is very small, that means that the way this thing is arranged, this is 1, 2, like 1, 2, 3, 4, 5. Okay? Or 1, 2, 3, 4, 5, 6, 7, 8. The bite angle here will give you what metal it's going to be abstracted. So if the bite angle is very, very small, what tends to happen is that they go for bigger metals, which is surprising. It doesn't go for smaller metals. It actually goes for the bigger metals. The reason for that is because the bigger metals tend to have what? A higher, they can be able to accommodate a larger bond length in terms of structural chemistry, okay? So you can see that this is one of them. So this is one of the structural chemistry. You can see that this is bonded, this is copper. It's bonded to how many bonds? 1, 2, 3, 4, 5. This is probably trigonal pyramidal structure, whereby you can actually see how the coordinate is done. The other one, you can see the same copper, but in this case, look at how it's coordinating. You see that? This is one of my molecules up, then the other molecule is down. Whereas this is, one molecule is binding to one. So they have a unique center. So what happens is that there's something else that can actually come into the center of it, and you're now able to move two particular what? Metals. And therefore you can actually be able to see that you're actually doing what? 2 or 3 metals coming in at the same time. And that one is again very, very specific. Let's move forward. Forward. Yes, this one is just an example. This is, you can actually modify the molecules. Move further. Further. Yes, you can actually modify this molecule from somewhere here, and then you have this one. So ditopic basically means that now I can actually be able to now use them, for example, for removing of nutrients, phosphates, nitrates, sulfates, such kind of things. So it's called ditopic because you can remove both the metal and also the what? The nutrients from if the water is completely polluted. This is just for mining, but you can actually use it for also that kind. Because we started first of all with mining, but now we can actually be able to apply the same technique for water remediation. That is wastewater remediation technology. Yes, next. So this is the last bit that I'm talking about. So the same molecules, we can actually put them inside nanomaterials. Just move forward. You can have different support. One of them is silica supported ligands. The next one is graphene supported ligands. You can have nanotube supported ligands, membrane supported ligands. I've had experience for all of them. I'm just going to talk about one of them. Move forward. So the support is very easy. You take an iron oxide nanoparticles, you synthesize it, then you put a silica so that it is encapsulated with the silica around it, right? Then you add the uptest. Uptest now gives it a functional group. Please go back. gives it a functionality, okay? So therefore you have the amine that Dr. Mobego was talking about. So once you have the amine, you can actually react it with the same salicylaldehyde that we produce from the first end, right? And then you have the same immune system. And so when you have the same immune system, what happens? Now you're actually able to use them for the same now remediation technology. So let's move forward. So look at that. It's very easy because this thing, the iron oxide nanoparticles are superparamagnetic. Superparamagnetic just means this. It means that the molecules in the presence of a magnet, they become magnetized. So without the magnet, without the presence of a magnet, they're just normal, just free-flowing particles. You see that? They're just free-flowing particles inside, right? But immediately you bring a magnet close to it, they all become magnetic, and therefore you can just basically be able to remove them, in a sense. And of course, this one is just a normal XRD that you can check what happens when you put those molecules, when you are synthesizing it. You have your iron oxide, you have the iron silicate, you have the iron silicate with the uptase, then you have the shift base, and you can see that transition going on. The silica is not what's it called? You cannot see it because it's amorphous actually. So since it's amorphous, you are not going to be able to see it on the XRD. The XRD will only work with something that is crystalline in nature. So we move next. So you can use what is called atomic force spectroscopy. That what it does is that it analyzes the surface of a molecule. So you can see that the iron oxide has got very sharp peaks. Then when you put the silica, what happens? The surface becomes a little bit softer. Then you have that is the TOS. Then you have the uptase, it becomes much softer. Then finally you have the imine, and the surface, by analyzing the surface, you know that you're making the right product. Next. Therefore you have the same images that we still had with Dr. Mobegi. So we'll just move to the next. Now this is HRTM. You can see that the shape of the iron oxide nanoparticles, which is hexagonal. They looked like they're round, but they're not. Then you put the silica, they start getting rounder. You add the uptest, they're much rounder, and then you have the imine, and therefore you can actually use them like that. Move forward. That you can do the elemental analysis if you want to for people who are doing organic chemistry. Next. So this is the extraction setup, where you have the molecule in solution. You put a magnet, you separate out. You can filter it for purposes of analysis only, but otherwise you don't need to. But for purposes, because the sensitivity of the ICP is something that is very, very important. So you filter it, and then you have that. Next. And of course, look at the extraction. Again, copper and lead, meaning that what? Even though they have been put on that solid support, they still act the same. You see that? So you actually have the same system that you can actually, now instead of putting it in hydrometallurgy, you're now using nanotechnology to be able to do the same kind of extraction. Next. This is basically some of the research that we're working on in terms of what is next. So we have green synthesis and study of effect of functionalized iron oxide nanoparticles. I think one of my students, Sarah is working on this one. Then I have histidine graphene. Histidine, I think, is an amino acid of some sort. Right? For us, it's just a molecule. We put it on top of a graphene oxide and iron functionalize, and then we use it as an abstractor. You have the resins that you can actually put it on top of polymeric resins, and it does the same effect. Then the other work that I have there, that is where most of my students are currently now, which is for degradation of selective pharmaceutical in wastewater using iron graphite, carbon nitride. I think Benjamin is one of my students working on that. Then we have shift-based ligands in the extraction of lanthanides. One of the things that we know is that lanthanides are very, very important. From your metal, from your mobile phone to your, like everything, including even weapons. One of the things that happened during this, what is called the fight between China and US, what was the first thing that China banned? Importation of lanthanides. That's why China did not care how much, US puts in terms of, the US could go as much as possible, but once they banned the lanthanides, because lanthanides are everywhere. You can actually get it anywhere. The problem is the separation of it. So one of the things, we've taken the molecules and we're trying to see if we can separate, because I told you that they were used initially for what? For actinides. So lanthanides is just a step above them. So if they are able to do that, then we can actually be able to get into that politics and see what happens there. Then of course we have the iron zirconium composite for endocrine disrupting pharmaceutical, which are very, very specific. And again, it's still nanotechnology, but we're using the same kind of thing. So I'll stop at that. So thank you so much for that.
Okay, thank you. Let's clap for him. Okay, now we invite the questions. Questions, burning ones, maximum of 3. Somebody? Somebody?
I've taken people to too
Okay,
much
Prof.
chemistry. Yes, Prof.
I just had a simple question on what you talked about, that angle there.
Yes.
So what about the idea of steric hindrance
Just
in
explain.
terms of when when the molecule opens up, if
Mhm.
you have a large thing that you're accepting, or are you bringing these metals in what solution? Because if the gap is not big enough, then you have steric hindrance, which doesn't help it to close up. Or did I miss something?
No, when I say the bite size, if it is very big, it tends to favor smaller molecules. Smaller, like the smaller atomic size.
So what comes into play here?
That is the bad side. What happens is that when you talk about structural chemistry, one of the things that you figure out is that if you have that very huge size, they tend to form, that bad size becomes a very big one. The bad size becomes, what? If it is
So the
big,
molecule is the one biting, right?
yes, but molecule is biting.
Okay.
So once it's biting, it can only bite, if it is small, it bites actually the bigger one.
Okay.
Yes, when it's big, it bites the smaller one. That is one of the things that we found out was interesting. So that therefore now you can actually now go and study the structural chemistry of it, and you realize that, for example, if you have a big molecule, because it has got a lot of, the valences are more.
So I can imagine if it's bigger, maybe it has many dentates, I can see why it's biting the small one.
Yes.
But I don't see the reason why the small one is biting the big one.
The smaller one tends to, because of the fact that, for example, if you want something like, let me say, a big molecule would be, a small molecule would be like something like magnesium. It has got two valences, right? So if they are so close together, the biting angle is very, very small together. What happens to the valences? What happens to the you get it? So the bond becomes much more strained, and that's what I think you're mentioning.
Okay.
They become strained. So you need it to be bigger, so that now the strain on the small molecule, because you see the most small molecules are also the charge in it is because of the closeness of the nucleus is also much stronger. So what happens is that you want them to be as far as possible. That's why they are biting the bigger one, the bigger one. Okay. Whereas for the bigger one, the nuclear force is much restricted because of the fact of the various valencies that are there. So you can actually have them very close together. So that kind of thing.
Okay, thank you. Next question. If there is none, then we move to the second presenter. Okay, thank you, Dr. Harry. So let's clap again for him. And I now welcome Dr. Hilary. Oh, there's something? Okay, so maybe they ask the questions first, then we proceed. Okay.
Yes, there is one on the screen.
Okay, it's already. Dr. Ogutu, come. So Dr. Ogutu is here projected. You can just answer those questions.
Excuse me, they need to hear, so if you use a mic is when they will hear you.
Sorry, the acids can be recycled. Basically, the whole system is recyclable. Anything, once you've taken the leaching system, remember the engineering aspect I talked about. It's leached, it goes into the stripping phase. The metal are released. Remember that the acid is what? The acid is like negatively charged, right? The metal is positively charged, right? They combine, right? Once they've combined, the metal is stripped out. What happened to the acid? It goes back to, again, use what? Abstract another, to be used for leaching of another metal. So you actually have a cyclic system that is continuously being recycled. So there's not much waste because you are recycling everything. The ligands are being recycled. The system is just recycled like that.
Any other question from online? Or those were that was the only one, eh? Okay, thank you, Daktari. So Dr. Rono has requested to present, then followed by Dr. Hilary. So Dr. Rono, welcome.
Okay. Yeah. Good afternoon. Yeah, good afternoon once again. Yeah, my apologies. My voice might not be that good. I think I skipped the tea session because we rushed somewhere for a brief meeting and then came back when we had already resumed. And then again, I have another meeting shortly running from 1, so I actually wanted to share just something small with this particular meeting here. Now, on my side, I wanted to sort of be non-technical because ideally when we talked about the School of Pure and Applied Sciences Symposium, I wanted to look at something that can cut across. But then again, you get limited because you would want to have some evidence. So I only looked at some brief aspect of what can make us visible outside there. Because I think where we are, the difference between the research moving from the bench to the market is ideally on the innovations. And I think as the theme of the conference, of the symposium, is that we want to champion innovations. So we cannot, we sort of are sort of trying to align the presentation with the theme of the symposium. Now, ideally, my background is in organic chemistry. So many a times I do a lot of organic chemistry type of research, and then natural products to be specific, phytochemistry, and I also do synthesis. But then on this particular space, what I've been doing since the time I sort of left the bench in synthesis is to try and make chemistry applicable. And by doing so, I look at some of the problems that are applicable to day-to-day real-world problems. So, so in my initial thought, I was like, I know with natural products or phytochemistry, we talk a lot about medicinal chemistry, and we at times interchange, or we interchangeably refer natural products to as medicinal chemistry, which is not the case. But then I was like, for today, let me look at natural products in terms of energy. So I'll be able to share a little bit about what we are doing currently in terms of energy. I think this one will put physicists into perspective. That's the aspect of renewable energy. Yeah, so we are working with a team. It's a collaboration project. I think, again, I'll borrow what Prof said. I've been out of physics space for quite a while. So if some concepts in physics come up and they are not clear, let it slide. Okay, that's what Prof had requested for biologists. I've been into chemical biology for quite some time, so now I'm back to physics a little bit. So we are looking at renewable energy. This is the solar panel, trying to harvest solar energy, convert it to electrical energy. That's the current talk, trying to be green, okay? So that we minimize a lot of pollutions that come across, that come as byproducts of the traditional sources of energy. And in terms of the solar panel, we are specifically looking at perovskite technologies. Perovskite technologies are some of the technologies in photovoltaics. And looking at the perovskite, I think for inorganic chemistry, Dr. Gutu will explain better what a perovskite is made of. But we are looking at the several layers in perovskite solar cell. And in this particular application, the essence now is to improve the various challenges that are there in solar energy or solar technologies is that the existing perovskites are having challenges on efficiency. The current efficiency is around 28%. A recent tandem perovskite got to 34%, but it's not yet at commercialization. So now, so in terms of perovskites, so we are trying to add into the engineering of perovskites by using phytochemicals in that aspect. So of course, this is the layer that we are interested in, where you have the perovskite itself, right? Yeah, so I know much of the stories can be told by Dr. Gutu on perovskites, but then let's move to the next slide so that I can explain where we are. Now, of course, this is the structure of a perovskite material. This the crystal structure. So you can see inside here we have a perovskite is sort of characterized by this APX3 structure. I thought I defined it somewhere, but it looks like it's not here. So where A is a large monovalent cation, B is a divalent cation, and then X is it's a halide anion. Of course, this is basic chemistry. I think all of us can relate with this one. Now, the beauty about this is to get an organic inorganic material that has good phototrapping abilities. And that's what we are really trying to harness and use that to transform solar energy to electrical energy. Now, the challenge with perovskites is that there are sort of limitations. So you cannot put any material inside there. There is a bit of material engineering, okay? But then in terms of design, where we are adding our input or contribution is in additive engineering, okay? So that's now the current shift in terms of technology. So we are trying to bring in phytochemistry into additive engineering. Next, please. Now, I highlighted an example that is in one of the work that we did. We reviewed, and then you have dodecanoic acid, that's simply lauric acid. It's a natural product. And then when it was used or incorporated into the additive for making perovskites, the ultimate result sort of showed improvement. So you can see the pristine device without any additive. Performance is right here. It's lower than the ones that have, the natural product. So you can see there is an improvement in performance. So one, you're adding an additive, the performance of the perovskite in terms of conversion of energy, that efficiency goes up. But then again, there is that question on stability. Remember, these are solar panels you'll be putting on top of your roof, for example. You want to harvest or trap energy as much as you can. So you also need to look at the stability of the material. So we have pristine here, and then the lauric acid modified perovskite. And you can see for some good time, around 30 days, you can get some percentage retention at around 88%. But then this other one drops to around 60%. So it means then one would want to look at additive engineering so that you can improve the performance and stability of these materials. Next, please. So now, what we sort of did is to sift through materials that have been reported so far. We went through several databases to extract some of the natural products. And you can see there are very few compounds that have been explored, mostly in the flavonoid class of natural products. Now, what we came to establish is that some of this hydroxyl group plays a role when it comes to crystal development. So that if you don't have it, then again, you might find that there is something called passivation defects in perovskite. I think for those people who are doing a lot of these renewable energy, they do understand. Now, so these defects, you will need a material that can fill up, all right? So one of the criteria has been, because it's a solar panel, you'll need to put it on top of your roof or somewhere outside there, then you'll need a material that is hydrophobic, all right? So that it doesn't mess up with the time. So there are several of these properties. So one of them is that it has to be hydrophobic. So you can see some of them are not hydrophobic. Their performance are good, but then their improvement, if you look at the summary that we did here, in terms of change in power conversion efficiency, not much can be obtained from these hydrophilic compounds. So you find that oleic acid sort of performed well. You can see gallic acid also tried in terms of performance, but then again, I think I did not specify here whether it was made of lead or made of tin. Some of them are made of tin, and they look like they are doing well, but then tin has a challenge again in terms of development. Yeah, so what we are trying to do in our case is to try and add on to this particular component. Now, there is a bit of results that we have gotten from some of the plants we are working with, but then I think I sort of caught up with time. That's why I wasn't able to share, because it's a lot of NMRs, a lot of UV studies and photoluminescence studies, all right? Yeah, so I just thought of sharing a little bit of it. Now, the second project that we are doing, and we sort of into it, is to try to do county-specific mapping of honey. And we are simply doing phytochemical screening so that we build their phytochemical profile so that eventually we can have a database that we can use it for information purposes. So what we do is that we solicit, we sort of source honey from various local sources, farmers from around, and then also the floral parts from around the same apiary locations. And then we screen them for phytochemistry. And then we also do floral sampling, and then quantification, and then spectroscopic analysis. Where we've had a challenge is here, because we only have UV that can assist us. So we were trying to do it at the level of GCMS so that we have some very credible results, but then the challenge has been the cost. So we've been trying to work around some collaboration with some guys from the Ministry of Mining who assisted us with one of the students, because they have a very nice GC, but then we aren't there yet, okay? Yeah, so I think that's just an idea on what we are doing in our second project. And then the last aspect in terms of innovation, I thought I can mention something on the importance of community-based projects. I think many a times, like what Prof has suggested, Eric suggested, and my chairman has sort of shared here. These are very interesting ideas. The only challenge is we haven't moved from the bench to the market. And I think that is where the gap is. So how do we bridge the gap between the bench and the market? So one of the approaches that we are trying to use as a department is to engage on community-based projects, and we are doing this collaboratively with organizations around, so that remember people, so that we can achieve ownership in some of the projects that we are doing. Now, remember, most of the community-based organizations integrate very well with the community. As we sort of away from community, even in terms of stakeholder engagement, we are usually neglected. Yeah. So I was in one of the organizations recently, and then I was asking them, why aren't you engaging the university as key stakeholders? But you see, they forgot that we have academicians, so they might invite one professor or two just to make it look like it's all stakeholders involved, but it's not really a stakeholder engagement. So one of the projects that we are sort of trying to partner is to look at solid waste management. These are project that is in the works, and we are trying to come up with an idea that can integrate the students and even some of the staff in the community. So one is in fabrication of materials, so that we take things like plastic, instead of disposing them, we reuse them, okay? We upcycle. I usually like upcycling because You can take the same plastic, you fabricate it or mold it to maybe a tile. Okay, you take plastic, mold it to some of the toy materials that we can sell. So in that way, we can come up with materials that we can generate some income with. Okay, so that can give us an idea in terms of innovations. Some of the ideas include these solid waste into fine chemicals. That's where I am mostly, and catalysis comes in. Okay, yeah. So when it comes to catalysis, there is a whole lot of opportunities here for organic chemistry and for inorganic chemistry, because for a catalyst to work best, it has to be designed properly by an inorganic chemist. So when it comes to some of these metals here, my idea was that if we can be able to recover, and that's where I was coming from, Prof, if we can recover some of these precious metals from e-wastes, okay, we can now take the same materials, because it's expensive to buy some of the very active catalysts. For example, rhodium. It's really expensive to buy, and for low budget economies like ours, we will end up not doing anything. So if we can recover from maybe our electronic wastes, then we can put in there and then convert those plastics to something good, fine chemicals or fuel. Yeah, I think that's one space I've been for some time. And then the other one is, other than the fuel, is community-based labs for water quality assessment. This is another project that we working with the community. I think I usually have a department on social initiatives for the department. And I've come to realize that the community might not benefit from us if they don't know what we are doing, okay? And by partnering with some of the community-based organizations, I have come to learn that they are even sort of advancing more than what we have as a university, because they already have some of these key instruments for their labs. So they can test the water they have mapped the water, groundwater for the community, and then they can always test for them. So what I only came to realize is that when it comes to standardization and calibrations, they usually invite the experts. So what I thought we can do as a university is to collaborate, and then we come in to partner with them. So as I conclude, part of the community-based labs, as looking at the mobile applications, this is an area where I am in terms of technology and physical organic chemistry, so that what we do, we can always generate mobile applications from some of these water quality assessment tools. Now, this is all about IoT. We get the right instruments, put it there, we can now monitor real time, as what Prof had suggested. So that's an area we can explore and we can try together. Finally, is on capacity building in an area where we are doing. Can we be able to capacity build? All right? Yeah, so that was just my suggestion from my end. I don't think I have any other slide other than that. Unless, yeah, so it's 8 out of 8. So thank you very much for the opportunity to present. And
a clap again, thank you. So now the forum now is open for question. Yes, somebody?
Thank you for the opportunity. I'd like Daktari to go back to perovskite material. That slide of perovskite. Yeah, perovskite. Yo, slide ya kwanza.
Can we please move to the slide on perovskite? Should be number 4, yes.
Yeah, I want to believe that a perovskite material is a semiconductor that has optoelectronic property to trap light and then use it to and convert it to, no, the light is going to eject electrons that will be used to generate electricity in that cell. Now, we are going. One of the materials I'm seeing there is lead ions or tin ions. You said there is a problem with tin, so most probably you will replace lead ions. I want you to explain how you're going to avoid the lead poisoning in the solar cell. And then there is these gaps that will be in a perovskite solar cell that are able to trap moisture and oxygen. How are you going to avoid that? And there is and what is it essential? The role of your additive. Is the role of your additive going to be used as the additive that you're using in a perovskite solar cell? Are you going to use it as a whole transporting or electron transporting layers in your perovskite solar cell? Thank you.
All right, thank you very much. That's a very nice question. I think one is on the role of perovskite in electrical conductivity. How will we manage wastes, especially the toxicity components or aspects arising from lead? That's the conversation right now. So that one, people have been trying to move away from lead. You know, the best performing has been lead. So you get MAPI, okay? And then now people have shifted to tin, but tin is kind of unstable. So they still go back to MAPI, all right? Or to lead-based. So, and that has sort of limited the commercialization aspect of it. Now, what is there which I've seen happening in the perovskite industry is that they are trying to have metal-free type of perovskite, but the performance has not been that good. I think I did see some work last year that they wanted to do a metal-free kind of perovskite, okay? But then again, the performance, the PCE, performance power conversion efficiency, was lower than the silicon-based perovskite, okay? Now, so that is why there is, in the current front, there is tandem kind of version where you have silicon versus, that is the pure silicon versus the perovskite, and then the perovskite, the latest one that was published recently by the Science is perovskite, which was at around 34%, okay? Yeah, so we would want to see how that goes so that maybe out of the developments, then people can now try to shed off lead in the architectural engineering. Now, what the phytochemical does is that it plays a role in terms of additive engineering. Mostly, when what they use in crystal engineering, when you are developing. Remember, these are perovskite. You've seen the crystal in structure, so you need to maintain the same structure. So if you change the molecule. If you can use any other organic molecule, but then the challenge has been most of the reported perovskite use synthetic molecules, all right? But then now going into the aspect of, synthetic molecules they are not that green. I'm a synthetic chemist, but I would want to say they are not that green. So we would want to come back to something that is renewable and more of green source of additive, and that's why we are into phytochemicals. Trying to tweak on its performance. All right. Thank you. I think I've answered. There were two questions, right? Oh, moisture and oxygen. Yeah, I think that's something on recombination. All right. Yeah. So it's something on recombination, and what happened was when you do the phytochemicals, for example, in the recent work we have done, we realize that it minimizes the issues on air, what happens when you have air inside it. And in fact, in our development, the colleagues in France that did the work did it at 88% relative humidity. So it was really, really humid, and the performance was maintained for like a month. So we are still waiting to see now how it does maybe after a while. So I think there is a bit of improvement in terms of recombination effects and managing dust and air. I think again I was lucky to see some of the developments with some group on telecommunication on how you can be able to get rid of the dust. But at least for air, we've managed that dust. I saw them working on something GSM technology to be able to clean up or to auto clean the solar panel. All right, thank you.
Okay, thank you, Dr. Roro. I think perovskite solar cells indeed maybe taking us to the next level in solar cell fabrications, specifically from the silicon-based solar cell, which is very expensive now. And as we can see in the recent past, this new research in perovskite solar cell is really going to take us to the next level, especially currently when it stands at around 26% conversion efficiency. So indeed it's really good. The only problem is the instability, which we are currently maybe trying to attempt and see if we can be able to have a breakthrough in getting materials within the same group of perovskites to be able to help maybe increase the stability of these materials. Otherwise, it's a good area of research in renewable energy. Thank you. We move to the next presenter. Let's clap for him again. Okay, next presenter, Dr. Hilary. Dr. Hilary.
Good morning. Is it still morning or is it afternoon yet? Good afternoon. My name's Dr. Hilary Kipruto. My area of study is phyto-inorganic chemistry, where I bridge between organic and inorganic. And I must confess that my research is like a next level for what Prof was talking about, where using the plant biomass to do the extraction of the metal ions. But myself, I'm going on the molecular level, where I use the molecules to extract the metal ions. So my title presentation is Innovative Bioremediation of Heavy Metals in Aquatic Ecosystem, harnessing polar crude phytochemicals for targeting extraction of metal ions. So simple introduction. We all know about pollutions. This is the contamination of the environment by toxic heavy metals. And these heavy metal examples are iron, lead, copper, and some of the sources are industrial, agricultural, and urban discharge. Next. The environment pollution have impacts on the health impacts, and this causes pollution and via bioaccumulation of toxic heavy metals. And this bioaccumulation of toxics build up in the tissue leading to harmful effects like neurological damage, cancer, disruption of biological system. Next. In our research, we're using these phytochemicals to do phytoremediation and specifically chelators. Phytoremediation is using of plant extracts to remove heavy metals for use of natural chelators as a extractor from soil and water. And next, just go. So these chelators are phytochemicals that are present in plant. As you can see in the schematic on the bottom side, you see the plant extracts the metal ions from the soil as it uptakes using the water, and it gets trapped using the phytochemicals in the leaves. Next. So as they get extracted, I'm giving an example of a molecular EDTA where it traps the ion as a complex using the chelating as what Dr. Guto was talking about, the biting of the ligands with the metal ions. Next. So in my research, I normally deal with the flavonoids, and example is quercetin, and on the right bottom side is a quercetin ion complex that I was able to synthesize to show you how those molecules bind with the metal ions as they do the extraction. And in the phytochemical chelation process uses phytochemical chelators to remove heavy metals, forming stable complexes with phytochelators. And these phytochelators are green in nature. Next. So in our process, in the experiment we did, we collected the plant material, dried, ground, extracted with the water, and then extracted the phytochemicals using rotavirb to get the dry materials, the flavonoids. And in our process of extractions, we do biphasic system, where you have two organic layer, mainly butanol, saturated with water, and then you have the aqueous phase where you have all the metal ions. So we place them in the table shaker, where we shake this biphasic system where the phytochemicals extracts the metal from the aqueous air and then forms a precipitate. Next. After doing the extraction, we do ICP-OES to do determine the amount of metal ions extracted. And we did this experiment at pH 5. And as you can see, the metal ions were in concoction were about 7 different ions. As you can see in the graph on the slide, you see that iron were extracted at more than 80%, followed by lead and copper. And we were able to find out that the highest efficient extraction was at pH 5. The efficient extraction of iron was the most from pH 2 to 3, going to 6. But for iron and lead and copper, you started at pH 3, going to 6. Next. In conclusion, phytochemicals have potential to act as a photoremediation of heavy metals, and they can also concentrate phytochemicals to determine effective extraction of lead and copper. pH also influence the pH extraction, where you have 80% of lead, followed by copper and lead. Next. These are some of the research I'll be doing in future, where I will use flavonoids to determine the toxic, the quantification of cyanide and mercury extraction. Also, we do quantification of flavonoids, fluorides, where since we use the flavonoids as a detector, where we use in conjunction with the metal ions. We also do research on edible oil, where you utilize flavonoids to improve shelf life of edible oils. With that, thank you.
Again, so we open again the forum for questions. Anybody with a question? Yes, somebody? Yeah, Professor.
So that's the question with the iron, the copper, and the lead. So from I'm not in organic, I think he's better than I am. But iron and copper are similar in size, behavior. They belong to the same clan. So, and copper is very good in coordination. So I'm wondering why lead will be preferentially uptaken or bound more than...
Actually, it's iron.
I mean, no, iron is number 1, but lead is number 2. I would have expected copper to be number 2. So I'm thinking between copper and lead, what makes lead, out-compete copper? Did you look at that?
Yes. If I can ask the person projecting to go back to the slide so that I can explain. Person in charge, go slide, go back. Back a bit. Back again. Okay. So flavonoids, these are general representation of flavonoids, and they have 3 chelation sites. This site A, B, and C. So for lead, just to recap a bit, the most active chelation site is the one circled red. And that one will always effective for the smaller molecule. What was Dr. Ezra was talking about, the bigger bite, smaller molecules. But for lead, it is on the upper side on the blue circles, and that is the least active. That's why it is goes for copper, for lead instead of copper. I don't know if I'm making sense. Sort of. Yeah.
Okay, thank you. Another question?
I just had a question because I'm looking at the molecule itself. That is the one that you are showing.
Just put it back again.
Yes, I can see that it has a lot of OHs.
Yeah, polyphenols.
Yeah, the polyphenols. So the question would be, those are very, when you're looking at hard acid-base classification, hard, soft acid-base classification,
Yes.
they would tend to move towards hard
More
metals.
hard because
Metals.
this is
yes,
hard
because
base.
of the OHs, because of the hardness.
Yes.
But then you have things which are soft like lead.
copper
so-
and lead.
Yeah, copper and lead. Why do you think that is so?
You see what? That's why for iron, since it's a hard acid, and this is a hard ligand, so it is preferential for iron. But since copper and lead are in the softer compared to iron, that's why the extraction is less.
Okay, thank you.
You has a follow-up? Just give me microphone.
Ion 2 is soft. Ion
Soft, yeah.
3
It's
is
hard.
hard.
Yeah, but
So-
for us, we are doing with iron 3 only.
Ion 3. Okay.
Yes.
Okay, thank you. Another question? Okay, I can see there is no other question. So thank you, Daktari. Clap for him. Okay, so we move to the next presenter, Dr. Ondari.
Yeah, we look so tired. I don't know whether it's because we've been taking in a lot of information, and unfortunately, a majority of them are mathematicians and they're not understanding.
Maybe Daktari,
Yeah.
a bit.
Okay.
I'm just getting requests from the online team that they are unable to unmute so that they can ask questions. So please, the technical team, see how you can be able to help those who are on the online. Thank you. Continue now. Continue.
I thought there are questions. All right. Kindly share my presentation. It's about 13 slides. I think I'll be very brief. Oh, it's already here. Allow me to start by saying that by listening the presentations today, I have actually realized that the Kisii University needs a school of nanotechnology. And we want to request that Prof kindly help us to actualize this. Because I'm also going to talk about nano, right? And that means we are quite a number of us, but then we've never known actually what we have done. And I also want to apologize that I'm not going to talk about what I did my PhD, rather I'm doing what I currently am actually focusing on. So my PhD was actually looking into the molecular mechanisms on how nanoparticles can be synthesized and what could be present in that. And as a biotechnologist, if we wanted to improve on those secondary metaplites to be able to synthesize more, what do we need to do? And then I actually applied them as nanosites against a novel acid Stefansi. So basically to talk about biocontrol. But then, you know, as a biotechnologist, I've realized that I'm expanding my wings, maybe because I'm young, right? So allow me to take a few minutes to take you through these nanomedicine applications, especially in infectious diseases. And there are quite a number of applications that we may be able to look at. So I'm not going to explain this so much because we now know what is a nanomaterial. That if you cut that piece of your hair 1,000 times, that is the size that we're actually referring to. Very small that you can actually not be able to see it with the naked eye. And the importance of that is that you can be able to create a structure or a device or a system that actually has novel properties, and that cuts across chemistry, physics, and biology. And that is why I said that, Prof, we have developed a curriculum in MSc nanotechnology covering the 3 areas. Chemistry, somebody from chemistry can do nano, somebody from biology or physics can actually be able to do the same. And we are also looking into whether you can actually be able to develop the one for PhD. And we hope that your knowledge will actually help us to be able to do that. And I also want to say that now that ability to be able to manipulate molecules at atomic level, which now can be measured to the nanometer scale, is actually what we basically refer to as nanomedicine. Next, please. Right. So if you look at that guy, a majority of us, we actually know him. We normally refer him as the father of nanotechnology. And from his divination that we can actually, that there's plenty of a room at the bottom, that is actually when nanotechnology was actually born. And because of that, there has been several inventions coming into, and you can actually be able to see that we can normally see that we have two processes on how we can be able to synthesize these nanomaterials. Either you start from the top going down, or you start from the bottom going up. And the basic one we normally do in our universities is going from the bottom, where you're actually building a nanometer scale. And that within that, there are three methods basically that can be used to be able to synthesize those nanomaterials. So I'm looking at Dr. Ketui looking at me. And the first one is actually the physical methods. So as a physicist, you actually can be able to come there. Then we also have chemistry, and we also have what? Biological. Now, when you look at all these methods, each one of them has some merits and demerits. For example, if I wanted to make sure that I have uniformly distributed nanomaterials, then in that case, I need to go either physical method or a chemical method. But then, are they friendly when it comes to other applications? The answer may not be very friendly to all of us. But then again, when we look now to biological methods, where I fall, we normally refer that as green chemistry, then you realize that you can actually be able to utilize either bacteria, a virus, or a plant to be able to synthesize nanomaterials because of the basic processes that normally undertake during the process of reduction. And with that, at least we have a hint on how we can actually be able to synthesize nanomaterials. Next slide. Yeah, so this is basically what I did. I may not be able to talk so much about this, but it is important to understand the process on how you can actually be able to synthesize and be able to characterize those nanomaterials. And those are some of the methods that have actually been given there. And at the same time, you can actually be able to see like what is really taking place during the process of synthesis. And on the other end here, you can actually be able to see how can we be able to characterize those nanomaterials by making use of different methods. And then, of course, the different applications that we have so far that have actually been reported when it comes to green chemistry. I mean, green nanotechnology. Next slide, please. Next slide, please. Right. That is the capping process essentially based on plants. So I was focusing on this because we've been talking about, making use of our resources from the environment, which we get so free and we don't pay for that. It's like that from that basic thing you're actually utilizing, then, a weed, like for example, a plant called as Tridax procumbens, can be used to actually synthesize this. So by utilizing that, anything, something that is not worthy, but at the end of the day, it's going to be worthy. That's actually the value we are adding into that by making use of what? The green chemistry processes to synthesize the nanomaterials. The other processes are also good, but they are actually expensive. We may not be able to afford them because we are still developing. I don't know what happened that we are not developed yet, right? So that tries to give us the different processes or the different compounds involved in making sure that you are able to have the process of reduction and that different compounds are going to stabilize your nanomaterials so that at the end of the day, you can actually be able to utilize them. Next slide. So I'm saying that nano is a double-edged sword. Sometimes today when I look back, in around 2010, when Kibaki was in the government, I was very happy that he was actually going to sign the adoption of GMOs. And at that time, I think I was in my first year master's. I was happy because I knew that by the time I'm going back home, there will be something for me to be able to do. But even as we speak today, in as much as we have only 2 approved crops in Kenya currently that we call as GMOs, we have actually refused to eat them. But then we eat them on a daily basis, but we don't know that those are what the GMOs were actually eating. So why am I saying that it's a double-edged sword is that it has its good side and also the bad side of it. But then we can't say that the benefits actually don't outweigh the effects I can actually be able to say. And because of that, there is actually need that we need to adopt this technology because of the main things it can actually be able to do. But then the big question we need to ask ourselves is that these nanomaterials have actually been shown to have increased reactivity, increased toxicity, and lower doses have actually been found to be toxic. And that's the major concern that we have to address as scientists today, so that we can actually be able to adopt some of these technologies. Because results that have actually been done indicate that when you do both either in vitro studies and in vivo studies, the results you actually get have disparities, which are actually significant. And that means that up to now, we still don't have what? A standardized protocol that can actually be able to assess some of these effects we are talking here, so that actually you can be able to utilize them. On the other end there, you can actually be able to see that there are quite a number of things that come into play to make sure that you are able to apply those nanomaterials. For example, size, shape, and charge. All these are very important. Now, again, if you look on the other end there are quite a number of processes that can be able to be used to actually reduce the toxicities of these nanomaterials to render them biodegradable once they have actually been utilized. And you can be able to see there at the center the different areas on how all those parameters can be able to be optimized when or depending on the need of the nanomaterial you are actually synthesizing. Next slide. So I'm asking all of us, like, what can we be able to borrow from this? Now that at least we have a hint what is nano, now that at least we are chemistry, biology, even including mathematicians, right? What can we be able to do? So if you look there, we have quite a number of areas on how we can actually be able to apply these nanomaterials. So I don't want to list all of them because my area was essentially focusing on what? The infectious diseases. So with that, allow me to go to the next slide. Right. For example, if we talk about the current treatment of malaria, you realize that in as much as we have a bullet drug, the artemisinin, being used for the treatment of malaria, it has actually reported in some countries like the Thailand and Cambodia, they have already actually reported resistance. And you know what happens when you use the last bullet and you realize that still the enemy is chasing you? What do? You have to run faster so that you can be able to survive. And the only way for us to be able to survive is to be able to adopt the nanotechnology, which now is going to combine the normal drugs we have from plants, and then with our nanomaterial can actually make sure that if we are targeting the parasite, we are able to eliminate it completely. Remember that resistance becomes because of what? When you use a drug and it's unable to remove the parasite, that is when actually it becomes resistant. But if you are able to, give smaller doses as required, and that you can actually trust me that at the end of the day, you can actually be able to kill that. And this has been the major issue that we're actually looking at. So malarial drugs, they have actually been found to have low oral bioavailability. They have short life. They are not specific in terms of the targets they are actually targeting. They have also been shown to be resistant, and the most important thing is they also have been actually shown to have poor pharmacokinetic profile. Now, when we marry this nano that we are actually talking about, then you realize that we can actually be able to improve the activity of the current treatment that actually we have for all this. So this is just part one for the treatment of malaria. There are quite a number of those such drugs that have actually been used. Like, for example, there is this common drug used for the treatment of cancer, right? I don't know whether we know it. Chemists? Yeah, we might be able to know it because it has been isolated from a very basic plant, right? Doxorubicin. Yeah, so that is the drug. And that can be able to be used and to be able to be improved. And that by actually making sure that, we have all that, then you realize that we can actually be able to overcome some of these demerits that they actually have. Now, when we talk about that, then what comes into mind is that we can be able to make use of either liposomes or the polymers or the dendrimers or the polymeric hydrogels, those that have actually been listed there. And they have actually been found to be very effective in making sure that we improve the usability of the existing drugs. Remember that were it not for the information technology, we could not be having a course called as bioinformatics today. And if it was not bioinformatics, then that means that still developing a single drug can take 15 years. From the time you want to develop one until you are able to get the approvals, it actually takes 15 years. But because of this technology we are talking about, now we can be able to have a drug even within 3 months, right? And that is the case for COVID-19. Everyone will be dead by now. But because of what? The technology that we're actually talking about, we are actually able to have real-time solutions. So we are not saying that nanotechnology cannot be able to deliver so much. It can be able to deliver if only we sit down and understand like what do we want and where are we actually going. Next slide. So I gave few of those. Like, for example, if you talk about polymers, you know, there are drugs that can be attracted to either hydrophilic or the hydrophobic nature. And so you can actually be able to encapsulate that. Now, the good thing with this is that this is already natural. All of us, we know what are polymers or what is a lipid, right? Yeah. So by using this simple technology, you can actually be able to do that, and we can actually be able to improve on how those drugs are going to be absorbed into our body systems. And if they are absorbed correctly, then that means they are going to be efficient. And the efficiency is what we're looking for when it comes to treatment. Next. Yeah, on the other one, we're talking about the polymeric nano materials. And you can actually be able to see that A there is actually the nano structure we're actually talking about. And the B component is the I'm saying there, is the red blood cells. And so you can actually be able to see that the nanomaterial is getting attached into the red blood cell, and once it's there, then it can actually be able to kill the red blood cells because they are the ones which are actually going to kill the parasites. And if we go to the next slide, you will be able to understand that still we can be able to make use of the dendritic structures. And that is why you can actually be able to see that we have either a single molecule which can still be encapsulated into that, and then still it can be able to be uptaken through the normal cell membrane so that it can actually be able to reach the target site, and then it can be able to be utilized for that purpose. Next. All right. So I'm saying that, you know, the biocontrol of making use of this nanotechnology is it has different sides or ways on how it can actually be able to work. One is either it can be able to target the cell membrane, or it can be able to target the enzymes within the cytosol, or it can be able to, you know, denature the membrane itself, whereby the cell constituents will come out and an organism easily can be able to be killed. Next. So, if you look, for example, that malaria drug we're actually talking about, it can actually be able to take 3 stages on how it can be able to be used. Either you're going to take a drug directly to the blood where you can be able to get it via intravenous, or it can be able to be done directly to the liver or to the capillaries, or rather it can actually be able to combine both. And that is actually to make sure that wherever the parasite is residing, you can be able to successfully target it and eliminate it completely from your body system. Next. So, this is where I am currently, and that is why I didn't want to focus on what I did on my PhD. So, one of my PhD students actually has developed a tool for diagnostics using aptamers and nanotechnology. So that's one of the area I'm actually focusing. I'm also focusing on drug delivery. We are also currently trying to develop some of the using the natural products we have, and we are trying to see whether they actually can be able to have an impact on mycoplasma. So I'm also looking into that drug delivery thing. Then I think I'm also looking into infectious diseases like malaria and other diseases that actually we have. But then that doesn't mean that I'm limiting myself to the 3 areas that I've already talked about. Still, these are quite a number of areas where we can actually be able to look at, and then we can actually be able to improve our health. I can say people like all of us, we can actually be able to do that. Next. Right. That diagram is really complex. but I want just to talk about 5 things from there. So if we are to succeed, then we have to look at how can we be able to How can we be able to deliver our drugs? So we're talking about genomic editing, then we're talking about these other components we have here, like for example, modulating the immune systems. We can be able to talk about, being able to determine the final pharmacokinetics profiles is actually very important for you to be able to understand how we can be able to deliver that. Now, if we were to focus, or if you were to go back and assess yourself, like for example, I have this nanomaterial and I want to use it for maybe as a drug. How can I be able to improve on that? Then you actually have to think about all these things we have on this circle here. So starting from the exterior, then we have the is it the mantle? Yeah, and then we have the inner core there that is actually going to affect all of us. And I think with that, I will be able to say that is my presentation. I don't know whether we have a next slide. Yeah, maybe conclusions, quick ones. I'm sorry for that. So what I'm saying is that it is offering quite a number of opportunities in terms of actually improving the prophylaxis as well as the therapeutic purposes. And we can also be able to improve the solubility, biostability, toxicity can also be able to be controlled under that. And we can also be able to actually overcome resistance. Right now, if you realize, since Trump came into office, there is no funding to AMR, antimicrobial resistance. And that means that actually all of us are going to die at some point. And we are dying soon because of what? You become sick, you go to the hospital thinking that you'll become well, you end up actually dying, right? So we need to think out of the box. How can we be able maybe to use what we already have, but improve on its efficiency? Lastly, it's also important we also need to engage the pharma companies, public and the private sectors to be able to improve on this. And I can be able to say that majorly because when the concept of biotechnology was being born, it was actually being born at the lab. It was never taken to the end users. And that is why that in as much as we're talking about we want to commercialize what we are having in the lab, we also need to break it down to the common man out there, understand this technology, how is it going to be useful, such that when you launch your product out there, it's already accepted. Thank you so much. Questions?
Yes, questions? Questions? Clap for him again. Thank you. Questions?
So, Prof, you put me on task more than once. So, let me first make a comment and then a question. Yes. So, nanotechnology, nanomaterials, and the nano idea has been running for a minute. But I like where I see it, especially Kisii University and quite a few of places. We made a tour last week. I went to Egerton and where did we go? USIU. And that was also running anti-research, especially at the institutes. Nanotechnology was a big deal. One of the things that happens in the US is creation of centers of excellence. So, and I think I mentioned this to the chair some time back, and I don't know who they were with. Kisii University can be the place for the Center for Excellency in Nanotechnology. But Kisii University has to show cause why it should be the place. And you can be, but usually things are driven by numbers. So I think the task becomes for you guys in the nano, in Kisii University, and I'm willing to partner with you to push you, but you need to get the numbers. How many chemists are doing this thing in the country? Find them. Have this list. Put them on a map using your GPS. How many biologists are doing this thing? How many guys in nanomedicine? How many guys in the materials and physics? Once you put them on the map, now you begin to have conversation with some of them. And you give them you give them ideas of what you have. You want some buy-in. So the way the center gets developed is that you have this idea, you buy in these guys, so that when you are now writing a proposal, whoever is looking at the proposal says, you're not going at this solo. You have actually engaged these other guys.
Yes, sure.
They are actually on board in you doing this, and it's not going to just benefit you, it's going to benefit everybody. But you've taken the initiative, they are agreeing with your initiative, there is no reason why you will not be funded. That's my comment on that one.
Thank you, Prof.
And on the other side,
Yes,
so there is some groundwork to be done.
Yeah.
And you'll be surprised. Funding comes very easy when you have those numbers. I promise you. Now, the idea of precision medicine, it's the big thing now, even in the Western world.
Yes.
So that now, having looked at the genome, I should be able to go to the hospital. It actually costs about $1,000 just to get my signature of whatever. And then it tells me what I am likely to be prone to, right? So
it's called personalized medication.
Personalized medication, that's correct. So the idea then becomes, as we personalize the medicine and we are going down to the nano and we are understanding more how the drug is and the receptor and your body tendencies are, that's a very good conversation. So my question is not even scientific. It is, I know that conversation is happening somewhere in the Western world. I've been into some of the forums, especially in SoCal, where we were having this conversation. And I was actually very leery of where medicine was going, because I convinced my family members, I have 2 of them in the medicine and they're actually finishing to start practicing. And I say, they're going to kill me because now AI is taking over. They are just going to be interpreters of what AI is saying.
Yeah.
Okay, but where is that conversation taking place in this country?
All right. Right now, we actually have a forum we call as the African Synthetic Biology. So if you are able to visit that website, we have that serious conversation there. It is a small group that started recently, and so far I think we had our 3rd conference in Rwanda just last week. And we hope that it is usually taking shape around the African crop. So I think maybe discussions have to look into what you are actually telling us, that we need to expand our niche from Kisii University, map out who can actually be able to work with us, and specifically maybe focus on more on what currently synthetic biology Africa is actually doing, so that together we can actually be able to integrate the precision engineering we're talking about, the nanomaterials. Yeah, we do invite them, specifically when we talk about the gene therapy. They are part of the team. Thank you. Another question, please?
Yes, thank you, Dr. Ondari. I know you were my lecturer in nanotechnology during my PhD coursework. But this thing that I didn't quite understand is, you said that they are using even nanotechnology to treat cancer cells. And I don't quite get it, how they do that precision delivery targeting to those tumors without affecting other cells.
All right, it might take a little, but let me say this, that when you're making the nanomaterials, for example, if you are going to have triangular nanomaterials, they're actually very effective in terms of, they have a base where you are able to attach your drugs. And then you can actually be able to deliver them directly to the cancer cells alone. Because the major effect with treating cancer is that the drug does not recognize that this is a normal cell and this is an infected cell. So it ends up digesting all good cells and bad cells. And the side effects actually are the ones now lead to death. And for us to be able now to overcome that is to be able to know how can we be able to deliver specifically this drug to only a cancer cell. Remember that we have biomarkers. These cancer cells, they actually express different biomarkers. So you can be able to give them a biomarker because it is something you can be able to check from a laser, and then you are able to, just like when, I'm sorry to say this, but when you go to the hospital, they normally do an ultrasound, right, using lasers. And that's how you can actually be able to comfortably identify that this is the cancer, this is where my cancer is, and then you can be able to, deliver your target drugs to that specific cancer cell. In that way, they actually become more effective. So here we're talking about targeted drug delivery. Another question? Right. I guess there are no more questions. Thank you so much.
Daktari, I'm sorry to say this, but I want you back there again because of the fact that you are chairing the next session. So please, I think the next presenter should be Bethwell. You can introduce him.
I left my phone. I've been chatting actually with him. I don't know whether he's ready, but I'd request that instead of wasting time, we can pick anybody who's ready to start, and then we give him, he's ready. All right. Doc, please, welcome to this, and we are going to give you 10 minutes. You tell us what you're doing. You'll have a few minutes for questions, and then we call it a day. So welcome. Take over. Brian, I think you can look into that. You let him speak so that we are listening.
Hello? I'd prefer to have my presentations shared from your side.
All right. Have you
I already sent it to Marumbu.
Okay. I think
Edgar.
he's working on it.
They're trying to upload it?
Yeah.
Very good. Thank you so much.
So we'll give you exactly 10 minutes, and I know you
I will work in less than 10 minutes. Thank you very much, Chair, my able chair. And thank you for your presentation.
Thank you, sir.
Yeah. So before I begin, maybe let me just say something, so that we can buy that time. I want to say that the presentation that I'm making here is just to stimulate us to ask questions. Just put it on full mode. It's okay. Put it on full mode. Full presentation mode would even be better. Full presentation mode. Thank you. Thank you. So here at the Biological Sciences Department, which is a sister department to the Chemistry Department, our association, even in the field of science, has resulted in a very interesting possibilities. One of them is a subject area called biochemistry. And I'm hoping that even as we push on time, our relationship with the physics department would also be as much stronger, so that we'd have what we call biophysics. Now, if you look at our presentation, it's entitled Exploring Local Ethnopharmacopias for Innovative Health Solutions. And there's a big team there. And in this team, this is what I want to insist, to really stress on. That within the Biological Sciences Department, there's a team of very able people with capacity in different skill areas. You can see we've just had a presentation by our chair, Dr. Ndari, who's in biotechnology. We have people in botany, we have people in microbiology, we have people in biochemistry, we have people in ethnobotany, and even parasitology. This means that if we can work closely with the chemistry department, there could be very interesting outcomes that would help us to push forward the agenda of Africa and improve the lives of our people, particularly at community level. one of the things that this paper highlights is trying to look for, one, areas that we can work in together. And indigenous knowledge or traditional knowledge, which involves the use of medicinal plants, is one of those areas. That is why we are talking about ethnopharmacopoeias. Next. So the traditional medicine, without a doubt, is very, very important. And medicinal plants are actually the backbone of our traditional medicines. And what we did to exemplify or demonstrate what we can do with you, the chemistry department, is that we went and did what we call a literature review on our local environment where we are in, southwestern Nyanza, where we have about 4 tribes, 4 ethnic groups, Luo, the Kuria, the Kisii, 3 ethnic groups, the Luo, the Kuria, the Kisii. And so we did an online search, and we used a method. So just move to the next slide. And our main focus was on antiviral plants that are used for treating viral diseases. The southwestern Kenya area, as I've said, is within this western south part of Kenya, and it's very rich in plant diversity. It also has very, very rich, strong traditional medicine use. So we can move on next. So what I said actually is that we want to demonstrate that there's something that can happen between these two departments. So we went out, looked at this data, used a framework which is acceptable for what we call systematic reviews. Yes, we ended up with very little data, but what we have can exemplify that actually something can happen between us. So our sources of data were basically from academic databases and also from grade literature, which we were searching using Google Scholar. And we were using only English as our main language. Just move on, next slide. So the search terms were antiviral. Then we also had how we would decide on what we would take in as data for these 3 communities that are found in southwestern Kenya and the plants that they use for antiviral diseases. And then we are only excluding plants or sources which were not either plant sources. There were blogs which we could not verify or did not have references. We also had places where we had duplication of those data sources. So just move on next. So in terms of results, we have very interesting results. We have purposely divided them into the 3 main groups that are found in southwestern Kenya, the Kisii, the Luo, and the Kuria. And if you look at this, basically we have a column for bioactive compounds, references that have been used to get this particular data. And then what comes out very interestingly is that we have data for the references between 1978 and 2025. And in terms of the bioactive compounds, a very, 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 very diverse array of chemical compounds in different chemical families. We have coumarins, we have alkaloids, we have terpenoids. We have all these different groups of compounds which link to something that actually most of the traditional medicines sometimes act in a synergistic way to alleviate some of these conditions that we are talking about. Let's go ahead. Let's go ahead. For the Kuria, and I also want you to note this, that some of the plants are repeating themselves. Maybe that I'll talk about when we're talking about the patterns. It's a similar pattern again in Kuria antiviral plants. And you'll also observe again a diversity of chemical families, chemical molecule families. We also have a number of diverse references, some of which are very, very recent. Go ahead. And then these are the ones for the Luo antiviral plants. Again, a similar number of repeated species. You'll note Xanthoxylum, Calibium, Todalia isatica. It's also found in the other 2 results for the other communities. Let's move on. So these are the plants themselves in terms of pictorials, how they look like. Very beautiful plants indeed. Let's go to the next slide. Let's go to the next slide again to see the patterns that you normally expect when you're dealing with any ethnopharmacopoeia. Particularly, I'm talking about the African ones, which would be very, very critical to us as we look forward to getting new molecules which could help in healthcare. So what we notice first is that there are several cross-community consensus on the usage of plants. You'll find that, for example, these 3 plants are used by both communities for the same thing. The next thing, some remedies are community-specific. You don't find them in other communities. Just move back, move back. Then we have, again, confirmation of activity through the chemistry, that actually some of these constituents of the plants could be useful in alleviating those conditions that they're used for in traditional medicine. Then also we notice this, that most formulations that are used for antiviral conditions are a mixture of many medicinal plants. They are polyherbals. And their dosages are normally determined by the healers. Lastly, again, we also observe, based on the trend, that there are some molecules which could be likely candidates that have not been tested for their ability as antivirals. And they can also be potentially used for other studies that could also help us to innovatively see their activity through either docking studies or other toxicity studies. Move on. As we conclude, I think the most important point here is that we need to integrate the chemical and the biological sciences, and even the physical sciences, to help us to come up with new antiviral therapies. And I think this is the thrust of what my presentation is in, that we have a lot of potential. We have many areas that we can collaborate in that will help us to come up with new drugs. Let's move to the last slide, which talks about the key goal areas. I'm sorry, that the last slide, the key collaboration areas. It's okay. Key collaboration areas, last slide. And I'm ending my presentation, last slide. So, looking at the chemistry department, there's a lot of capacity in the chemistry department which we can leverage on. I know there are a lot of natural product scientists in the chemistry department. And some of the skill sets that I'm talking about here are areas where if we work together, there could be a lot of synergy that would lead to new therapies. And these therapies would change our economies. Because remember, a lot of drugs that we are using currently are coming from foreign pharmaceutical companies. Now, one of the areas is phytochemical analysis, structure elucidation and modification. And here I'm very interested in what chemists are able to do. When Dr. Dutu was talking about the para position, the ortho, the meta position, what happens if you put in a chloro or a halide into a molecule that already has activity? What happens to it? Then drug formulation and stability testing, bioassay guided fractionation, standardization of herbal products, and very importantly now, how can we accelerate the discovery of new therapies? And again, here we have new possibilities, new tools, machine learning, artificial intelligence, docking, yeah? Then we also have what we call the possibility of having what we call hubs, innovation hubs, which are interdisciplinary in nature, where we can work with pharmaceutical companies, hospitals, to come up with interesting new therapies that could help in our societies. With that, I want to say thank you very much, and I'm open for questions.
Let us give him a nice clap for the presentation. Thank you, Prof. Ogor, for the nice presentation you have done.
Edible vaccines, yes. Biotechnology offers a lot of opportunities in terms of therapies. We have relied a lot on in our pharmaceutical chest. We have relied a lot on plants. They still are a source of new therapies, but again, genetic modification, the possibility of introducing the real proteins into the plants and having them taken in is a real possibility. And these are all open as we look at possibilities that are there to improve healthcare at the local level. I really thank you for that, because this is not, my focus was not on this, but those are very, very exciting areas. Even the use of the genome, understanding the genome, we can have what we call predictive medicine that can really help you even to know what you're likely to suffer from in the future. Thank you very much, Dr. Moore.
Thank
this
you.
is,
We have,
this
I
is
think,
it.
one more burning question from Professor Mwebi.
So the molecules that, and of course there is, maybe this question is coming out of quick thought. So when you are doing docking, for example, you would want to have a fairly clean molecules. So how easy is it for you to isolate this, if you have done it, these molecules, and then be able to really get their structure and do some docking, either you or somebody else? Because that's a little bit of bioinformatics.
Yeah, thank you very much for that question. What I would say is this, that some of these new tools that are being used, as you've said rightly, require you to very, very clearly have the structure of the molecule. And in those experiments, look at the energies or the interactions that they have with the molecules that you have of interest, target molecules that you have. And I'm saying chemists have a very, very big role in this. I am a biologist myself, and I would say that the collaboration between chemists and biologists would help in coming up with very refined results, which would help in frog leaping these possibilities that are there.
Thank you, Prof. I guess there's there's one more burning question again from Dr. Guto.
Yes, thank you so much, Dr. Ari, for the presentation. I feel a bit jealous that you guys thought of this before us, and yet I know of so many natural product chemists here who would want to be associated with that. So one of my questions was this. Having done nice work like this, is it possible that you could look at similar plants that now are available in those particular localities? Then we see which ones can actually be, one, cultivated, or if not cultivated, then we can see how biotechnology comes in, that is in terms of genetic manipulations, to try and increase their potency. Is there anything like that that you've seen? Thank you.
Looking at the future, thank you very much, Dr. Guti, for that question. Looking at the future, we have to think of how to sustainably use our resources, because there's a possibility that when a species becomes earmarked as a useful species for therapies, and if it is in the wild, it's likely that it will be over-harvested. Again, there's a possibility that there would be chemical moiety in the plant that would be active, that would be the active ingredient. And the amounts that are produced by that particular plant through its metabolism are very, very, very limited. We can tweak the genome to ensure that pathways that produce these drugs are actually upregulated, which means that the products that we are interested in are produced in amounts that are actually commercially viable or just good enough to give therapies to our communities. So you're very, very right. We've not gone to that stage where we have, and some of these plants are really common plants. We have not gone to that stage where we are going to really look, we have looked at what they have in terms of their potential. But those are exciting areas that we could shoot out into as we try to look for areas that we can build on our collaborations and also expand the possibilities for new antiviral therapies in the future.
Thank you. Thank you so much, Prof, for that insightful discussion we've had. And I want to thank you so much for that. I think we are ready to usher in the next presenter.
Thank you very much, Chair. Thank you very much, the Chemistry Department for the symposium. Really, really appreciate. And thank you for any collaborations that could possibly be there in the future for the two departments and many other departments.
Sura yako na kwangu, raha zako kutazama, mahaba yako ndio tiba yangu na moto yako kwa. Ni kitu gani unaniletea maringo, ngoja kuumiza matumbo. Mimi ni msanii tena chali wakishua, ukipata kunijua utagundua mimi mtu wa maana, na sina time ya kupuliza gunia. Ni duara hii dunia, nakwambia utajileta. Haini mama, mshowe mama ua. 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 Pare bila pesa kidonda, cheki demi kona kutoka, wananipenda Maradona, jumu wapata nikisonga. Usipandishe mjembo boda boda, yondo siku mwisho utamwona. Usilize kani ligonga, niulize kile niliona.
Tech Equity Capital Management, IP Value Management, and British Technology Group, BTG. He has served as an adjunct professor at Dedan Kimathi University of Technology, and he has taught courses in entrepreneurship and research methods. Sounds like something somebody was talking about. We should start. So Kennedy, or Dr. Obare, holds a PhD in optoelectronics from University of Cambridge in England, and an MBA in finance and business strategy from Georgetown University. He is fluent in both English and German. So if you want to ask him questions in German, welcome. So it is a great pleasure to introduce our next speaker, Dr. Obare. I think he's based in New York. Actually, I think it's New York, Boston area. So it should be very early in the morning. I don't know what time it is over there, but he can let us know. Dr. Obare, the ground is yours. IT?
Okay. Thank you very much for that introduction. Again, my name is Ken Kennedy Nyairo, and it's a pleasure to speak with you today and on innovation and technology transfer and intellectual property. And I chose this topic because I thought it could be very interesting for you, and it's probably very different from what you are discussing about. But I believe it's a very, very important subject. It's a very broad area, so I have only 30 minutes to talk about it. So my presentation will be very high level. It's very difficult for you in 30 minutes to cover any greater detail other than just to put the subject in context and frame the ideas and hopefully stimulate some discussion. So in terms of the agenda, I'm just going to speak a little bit about what we want to achieve here. I'll talk about innovation in Kenya. I'll talk about technology transfer as a concept, and then talk about intellectual property basics, and then look at some of the innovation success stories in Kenya, and hopefully then can stimulate the students or other entrepreneurs to really get involved in this area, because I believe it's a very, very important area. I have been working in the area of intellectual property and technology transfer for very many years, as you might have heard from my introduction. So I'm very passionate about this area, and I think it's a very important area in the sense that without innovation, seriousness in innovation, no country can develop. Most of the developed countries that have really grown and continuously continue to make progress in technology areas, in pharmaceuticals, and many, many other areas, It's just because they focus on intellectual property and technology management, as well as innovation and entrepreneurship. So this is a very, very important area. But first of all, let me actually begin by just presenting a little, and probably you know it, but just to think about it a little bit. What is innovation? Innovation is indeed a process of turning ideas, concepts, thoughts into value, generating value out of ideas. That's just innovation. And innovation can take many forms. It can be innovation at the product level. It can be innovation at the process level. It can also be innovation at the business level, business model level. Even it can be innovation from social aspects. Therefore, with innovation, many countries are making a lot of progress because they're making progress in either end of those areas I've identified: product, process, business model, and coming up with new ideas and implementing those ideas. Going forward, let me explain a little bit what the concept of technology transfer. Basically, beginning with research until there is a product that is used by the public for commercial use. So here in where I work at the University of Rensselaer Polytechnic Institute, basically we have many researchers turning ideas into ultimately into products. The concept really begins by spending a lot of money on R&D research, and this money comes from either the industry sponsorship or from the government. The government spends a lot of money to most universities, engineering universities, technical universities, or science universities to conduct research, and both in the life and the physical sciences. And in my university, for example, we spend annually $100 million just coming in for research. And this comes to the professors who then conduct research with the students. And from there, they come up with new inventions. And when those inventions have come up, my department, which is the Technology Transfer Office, go back, I'm not completed that, the previous slide. If you can go back with the slide, please. Yes, yeah. So if you can go back with the slide, yes. So now from when the ideas come from the laboratory, an invention comes, it's reported to us in that office, the office that I lead, and we call those invention disclosures. When they come, it's my duty with my team to assess whether that is a good idea or a bad idea. In other words, is it an idea? Does it have commercial potential? Does the idea have possibility of getting a patent? Because there are regulations around ideas when you're patenting, getting patents or protecting those ideas. So we do IP protection. We analyze those ideas, conduct a serious assessment, and then from there, we either license those ideas into companies, or those ideas become the basis for a startup company. And then from there, of course, the technology is then commercialized and ends up in the public use. This process is fundamental in technology transfer. And it's a continuous process. And when the technology has been commercialized, the professors end up in getting a share of the revenues that are generated from that technology. And so this is, I think, extremely important because you're trying to bridge research and then into real world applications. It's important. You stimulate economic development, and then you end up in also creating jobs. One of the situations that we have in Kenya now is that we have a very high rate of unemployment. But I think if we went into this area of really using technology to start companies, we may be able to reduce unemployment to some extent. And basically, so the most important thing is that typically there is a government involvement to some extent. There is university and industry collaboration, as one of the presenters mentioned earlier on. And we have also seen this in Kenya. These are actually very ideas that are being taking place in Kenya. In fact, if you can go to the next slide, Kenya is been touted as the Silicon Savannah. In fact, it's one of the most advanced countries in Africa. But in the Global Innovation Index, Kenya is number 96. And so you can see that one of the reasons why the innovation index in Kenya is low is because of not many ideas that are generated end up in creating companies. They end up, yes, a lot of good work is done in Kenya with the very highly skilled, high quality work in terms of scientific advancement, in terms of innovation, but those ideas are not getting into the market. And therefore, the innovation index in Kenya is actually low for that reason. Although for Africa, it's probably one of the highest, it's one of the innovation in Kenya is really pretty high. But, but in terms of looking at the global innovation index, Kenya ranks 96 from I think the studies that were done in 2024. So Kenya is the Silicon Savannah because it's really recognized because of having significant innovation. Some of the key drivers for this innovation is obviously the government with very good policies. Also, some of the ideas that have come from Kenya that have been commercialized very well, like the M-Pesa, mobile money transfer technology, has really been an example that is used everywhere in the world and shows how innovative the Kenyans can be and can also participate at the highest level. And there are a lot of other areas where there are some startups like iHub, Gearbox, NILAB that are fostering entrepreneurship, but the rate of innovation and the rate of entrepreneurship is actually not very high. You can imagine that the Nairobi Stock Exchange has only 66 companies. And this number has not changed for very many years. In other words, we are not creating companies in Kenya. It's unbelievable that a stock exchange that has been there for almost, almost 50 years or so, has only 66 companies. So the other thing that there are quite a number of academic institutions, US included, that are also interested in this area a lot. And one of the drivers of innovation has also been the digitization of our platforms like eCitizen, where you can see that technology can be utilized to transform public services or access to public services. We have other areas that are of interest, like we have growth in fintech, agri-tech, in education, in health, and this will continuously increase services and job creation, positioning Kenya as one of the regional innovation leader. But let me speak a little bit about intellectual property and how important it is in innovation. When combined with innovation and entrepreneurship, you can really develop the country. So, what is intellectual property? This is really a legal right that protects whatever you have created. So this innovative idea that you have come up with, you have to protect it so that you can prevent other people from stealing it or taking it or using it. And so having a robust system protecting and managing this intellectual property is very important. So what types of intellectual property we have? We have patents, we have copyrights, we have trademarks, we have trade secrets. Like if you don't want to patent your idea and you believe other people will never know what that idea is, you may keep it as a trade secret. For example, Coca-Cola is not patented. That recipe that makes Coca-Cola is kept as a trade secret, and nobody has ever come up with anything near Coca-Cola, same as Coca-Cola, simply because it's a trade secret and it's protected that way. But it's important to patent ideas, new ideas, because ultimately you have that protection, and you can take people to court if they end up in infringing on your intellectual property. So intellectual property is therefore very important. It encourages innovation because you know that the technologies that you have developed are protected, and it also enables commercialization because you can use intellectual property, although it's just a piece of paper. For example, a patent is just a piece of paper, but it's a legal document. You can license it and generate significant revenues. In fact, most of the work I do is licensing patents to companies for the university IP. And so through intellectual property, you can secure a competitive advantage. For example, China is now the leading country in the world in generating patents because they're just patenting anything. And the US used to be #1, but now China has really overtaken the US in coming up with innovation and then patenting systems. So in Kenya also we have that. We have Kisii and we have Kekobo, so the Kenya Copyright Board and Kenya Industrial Property Institute. So, and there's several acts of that are really protecting IP in Kenya. So we have institutions. I think our challenge is now how do we move from just having institutions and then generating ideas that are protected and creating companies and therefore developing the country in terms of also creating jobs for our young people. Next. You may move to next because I have, one of the challenges we face in Kenya in terms of intellectual property is that it seems to be a very low awareness of intellectual property and the existence of intellectual property and the importance of intellectual property. There are also very few patent filings. Don't know exactly why, but I think maybe you will get to learn from this meeting why that might be the case. And then there's also very weak enforcement. In fact, the one very famous example is the technology that ended up that gives the blue color that is used in jeans that we wear came from Lake Naivasha originally. And the Kenya tried to, but Kenya never really protected the technology very well. And so some American company came and installed that technology and made and continues to make millions and millions of dollars. Now probably into billions actually, because jeans have been there for so many years. So there is weak enforcement. Next. We do have technology transfer in Kenya. For example, obviously, as I said, KEMRI is very strong and many other universities, but KEMRI is the one that seems to be very important. The mechanisms for transferring this technology from the lab to the market is through licensing, spin-offs, and innovation hubs that are now coming up very strongly. For example, carefree biopesticides have been commercialized and also various KEMRI medical technologies. I think essentially the law is very supportive. We have a framework in the country and we have technology transfer offices in general, but Also, the collaborative partnerships have generated a lot of IP that is ultimately commercialized. Now, challenges is commercialization gap and then very weak industry linkages. Industries typically really not fully involved with the universities in creating new ideas and funding and supporting startups so that ultimately we can make progress in this area. Now moving to the next slide. So linking intellectual property, technology transfer, and innovation is extremely important. Obviously, the ecosystem requires that universities, startups, and government and investors all work together in a way to be able to create a robust ecosystem for technology transfer. So in general, and to repeat again what I just said from earlier before, the research, IP, licensing, products, and market, that seems to be the general process of getting ideas from the lab to the market. There are several needs, as we have said. You need very clear policies. You need funding. You need incubators. You need skilled talent, and obviously stronger collaboration and enforcement will drive significant growth. Next. So in summary, benefits of innovation and technology transfer, job creation, technology startups to absorb youth talent. The new industries are also come out of this innovation, come out of innovation and technology transfer, increasing economic growth. And you get improved services because in essence, really innovation is getting something much better than what you had before. So as we continue to innovate in several areas in healthcare, agriculture, and finance, we will get improved services. And ultimately, our global competitiveness will grow as a result. Next, please. So there are several drivers I see in Kenya now that are really driving innovation. One is government support, and there is a policy framework. Second, the mobile technology penetration is very high in Kenya, and M-Pesa is one example of how financial inclusion and digital culture is now really very prevalent in the Kenyan commercial environment. And then there are startup ecosystems coming up. I don't know whether there is one in Kisii there at the university, or maybe they are. Then there is really academic institutions like Nairobi University, Strathmore, and others that are conducting research and have a strong innovation programs. The most important thing ultimately is that innovation has to be able to solve local problems and respond to unemployment, service delivery gaps, and resource scarcity. Next, please. So there are very many areas you can see where technology plays a very transformative role. And so that's, for example, in finance, in agriculture, in healthcare, in education, and in renewable energy. So these are areas where ideas that you generate in the lab may actually find use and application and can help drive innovation in those areas. We have actually quite a number of success stories in Kenya. There's M-Pesa, which you have mentioned several times. There is Hyperpack, which is bioplastics from water for eco-friendly packaging. There is another, there's I think another, and you know this probably, the Mkuru clean stoves. So this shows how people come up with innovation. There is Sign.io smart gloves. There is another one, Strauss Energy, and there's a gearbox. So all these are ideas that have come up from Kenya that are what one can count as innovative success stories. Next, please. Yeah, so what are the challenges? Next. Yep, I've covered those. What are the challenges in Kenya's innovation ecosystem? Actually, it's a challenge because there is very low research and development funding. It's less than 0.1% of the gross GDP. Okay, so that's too small actually. Should be much higher. There are gaps also between academia and industry. I don't think we have many collaborations as they should be. There is also the challenge of IP awareness and commercialization, where there is typically commercialization is limited. And the young innovators also lack mentorship on a large scale and also resources in order to start companies. So what I'd like to do in the next slide, please, is to have a challenge for the students to continuously participate in innovation hubs where they are, protect any ideas that you come up with. We have very nice organizations for doing that. Join up campus innovation and entrepreneurship clubs, if any, and pursue projects that really address local challenges. And yeah, so that is my short presentation that I'm able to do within the 30 minutes or so. And now I am open for questions, if any.
Thank you so much, Professor Kennedy Obare, for that insightful talk you've actually given us. And I want to agree to a number of issues that you've raised, that there's little awareness when it comes to IPR, especially in Kenya. And, you know, these days it has also become like a business. You know, like, for example, I'm doing my MSc, I have my innovative idea, but if I don't publish that, then I don't graduate. Or my PhD, if I don't publish, I don't graduate. But then it could be a very innovative idea that actually can be tapped into a patent. Maybe you can advise us on this as we look for more questions. So, thank you.
Yeah. Okay. So that's actually a very good question. And even where I work, we struggle with that because some professors are very keen to publish. The ideas they have come up with and don't want to wait and protect those ideas. But one of the ways in which we have mitigated that issue is involving the professors very early. So even before they're beginning to draft the publication paper, they have to submit that information to the technology transfer office, and ultimately and as we receive that information, we can file what we call a provisional patent application that is going to at least protect that idea for almost 1 year, and then they can come back in a year to file. We can file a proper patent application, but at least we have protected the idea. So that's the strategy we use in order to mitigate the publication issues with our professors. Yeah.
Thank you. Maybe a quick one as he's raising his question. Now that you've been working on the IPR sector, what are some of the funding opportunities that you can be able to advise or to tap into, especially to be able to have incubators and startups that can really help as a university?
I think the funding opportunities are many in a way. One thing is to encourage funding from the government to have very strong interest in startups. And funding can also come from the government. Funding can also come from private companies. And so that's the private industry really should participate a lot in terms of in terms of funding startups and investing, because for most companies, having a startup is almost like an investment. But ultimately, we have to encourage the rich people we have in Kenya, instead of keeping their money under the mattress, to really invest or in the bank or overseas to start investing in local companies. That will probably involve really motivating them, because there are a lot of rich people in Kenya who have a lot of money that is sitting there doing nothing, whereas that money could be helping startups. So I think awareness and education and really alerting them that there is money to be made also with startups. Yeah.
We appreciate. We have two more questions. Please go ahead.
Thank you, Dr. Kennedy, for such insightful things that you've given us today. I'm a PhD student of microbiology, and my work is on isolation of bacteriophages. I have found some bacteriophages that are novel, that have never been seen around. I don't know what happens when it comes to patenting natural products, whether you can patent something that you have isolated from the environment.
Yes, you can, because the process itself of isolating a molecule or a substance, that is, you can patent that, because that in itself can be novel. But you cannot patent a plant or something that exists in nature. So because that you did not create that, God created that. But seriously speaking, you can always patent any, for example, if you are involving substances or not, even if they exist naturally, but you have used a certain process to create something else, and that isolation process in itself is patentable. Yeah.
Just maybe to make it clear, I have isolated like viruses from the environment, but the one thing I've done more is to like form cocktails out of it to improve its use in therapy. I don't know whether that can be patented.
That can be patented. Definitely that can be patented, yes.
Thank you very much.
Yeah.
Thank you so much. Next one.
Thank you, Doctor, for your presentation. On the slide of challenges that we are facing to enhance our innovation, I have noted with a lot of concern that this issue of collaboration between academia and industry can have a far-reaching impact on innovation. Maybe what's your take on that particular point? What can you advise?
Yeah, actually, that's it's very important collaboration between industry and, for example, your university. The reason is the university sometimes may not have resources to fully commercialize the technology. Therefore, collaborating with industry, you may be able to do that, because industry typically they will have enough resources. For example, in biotech in general, this is extremely expensive. You need incredible resources in order to move a technology from the lab to the marketplace. And that typically requires a lot of funds. So collaboration with the industry is important. Here in the US, there are a lot of biotech companies that collaborate with the university. In fact, they fund research simply to get those new ideas, and then they can take them to the marketplace. The university may not be able to do it because the university does not have enough resources to do that. Secondly, the collaborating with the industry is significant because the industry tends to understand a little bit more the issues that are significant or important in the marketplace, because they're dealing with making products that are facing the consumers. So if having ideas in academia, sometimes there is that idea that, oh, I have come up with a great idea, and it's going to make a lot of, it's going to be so significant in the industry, but then you may not have the real knowledge of the steps required to commercialize that technology. So that's why collaboration becomes very significant. Yeah.
Okay, I also have a question. Prof, thank you so much for the talk. Now, one of the things that I've noticed, or maybe it is a cry in a sense, there is a weakness, particularly for the core sciences or the basic sciences, where our training has got an inherent weakness, such that most of us are not aware of how to, one, identify an idea that can be patented. That's the first one. Secondly, in terms of technology development or even transfer, one of these things is born out of the fact that I've dealt with Kenya in terms of one of our innovation. And I remember going there and I was being told that, you know, you have to know this, you have to know this, all these business courses that are supposed to be there. But then for the people who are doing courses, those was never taught as a basic education. So one, would you be able to advise on that? Two, would you be willing to partner with us as a university to develop a course or maybe a unit that can be taught throughout the university, like, okay, this is for IP or something like that? Thank you.
Yeah, no, I can definitely look into that. I mean, there's no harm in trying. So I can look into that to see whether there are opportunities for collaboration actually, and also maybe developing some coursework that can be very useful in bringing out this knowledge to the students. Yeah. Mm-hmm.
Last one.
So my question comes in, I want to make sure that it ties with the question that Dr. Gutu has just asked. So we want to make sure that this conversation goes beyond just being a conversation. So Kisii University is only about 10 years old. Is this right? Yeah. So it's a young university, but it's really running. And they have one of the highest enrollments, and they have a lot of promise. And I am conversant of the fact that you hail from Kisii. So I'm imagining that you do have an interest in making sure that Kisii University becomes special in a way. So the question I'm asking here is this. Okay, you have a framework. In fact, you work in, I believe, an office that is equipped with personnel that have a particular capacity, knowledge capacity, that are able to run an intellectual property setup so that the idea moves from just an idea to a company. What does that look like? Who do we need? And how can we begin so that 5 years from now, Kisii University, or 3 years, has that kind of office? Because one of the things that I have come to learn as I go from institution to another is people want to write a grant, but they don't even have a grant office, or the person running the grant office has never even written grants, has no idea, but they have a job. So could you give us an idea for that office and set up to happen? What do we need? Who do we need? Because it looks like we need people who know how to assess, but we also seem to need how to commercialize. What is it? Who do you have around you? And what does it take?
That's a very good, very interesting question. Actually, technology transfer from the university is a very complex undertaking, but it's straightforward in terms of the personnel that you need. In the first place, you need people who understand technology, who can assess technology, so that when these ideas are coming from the inventors or the professors, one is able to say, yes, this idea can actually succeed in the marketplace. So, for example, I use my skills in optoelectronics to assess similar kind of technologies very well. And then in the office, we have other people who are also very high level of education in the life sciences and others in the physical sciences. The other thing you need in an office, you need a portfolio manager. That's a person who manages all these technologies, because the process of patenting is not straightforward. it takes quite a number of iterations before you can get a patent. So you need someone who is conversant with the patenting process to manage the portfolio. Then you need other people who are able to license. For example, in my office, we have business development people who go out to now market these technologies and find out who is able to license the technology. And then you need people who are who are conversant in finance in order to be able to, as we commercialize these technologies, revenues are coming in. So we need people who are conversant with financial matters in terms of royalties that come in and how those are distributed to the inventors and also the university. So you need various components involving finance. We have a patent attorney in-house, for example, in my university, who is able to look at these inventions from a patent, a legal perspective. So, and then we have another person who is there to just see that we comply with the federal government, because we get a lot of funding from the federal government. So that is in general is what we really need in a tech transfer office. So in summary, you need technical people with technical expertise and scientific knowledge. You need people with financial knowledge. You need people with marketing and business development knowledge. And then you need people with legal knowledge. Yes. So in order to do that at Kisii University, you can start small. And in fact, you can even outsource some of the functions. Like, for example, you can outsource the legal function. You don't need to have a patent attorney in the house. You can use an external company, a law firm, for example, to do the patenting work. Yeah. Mm-hmm. But I think the most important thing is that there has to be a commitment from the university at the highest level that they are creating this office. And the interesting thing is, for example, in my university, the head of the university is very interested in technology commercialization. So there is that support for the office. Yeah. So you need that. That's one of the most important things you need in a university technology transfer setting.
Thank you so much, Prof. Obare. We really appreciate the comments you have given us. And I want to say that at least the university has taken the baby steps. We already have a policy. Maybe what we need to do is amplify, specifically looking into the government people and bringing all the stakeholders that we've actually mentioned into play, so that we are able to have a working IPR department. So, siamefanya kazi nzuri. I want us to prepare a nice clap to mwangushie tanda. Yeah? Nice clap. When I say 1, 2, 3, mwangushie tanda. Moja kubwa. 1, 2, 3. Thank you so much. We appreciate. I think we'll be able to keep in touch with you in case we need your, of course, we need your we need your expertise. We'll be able to keep in touch. And we thank you so much. Have a fruitful day, Dr.
Sure. Thank you so much. Thank you so much for inviting me for this.
Thank you so much.
Yeah. Bye-bye now. Have a great day.
Right. You too. So we are breaking for lunch, and I'm requesting someone to pray for us, maybe a lady. Unfortunately, we have